Okay, we're going to just cover one last thing in this video that, I didn't want to make that last video too long. So we're going to talk about, the same thing. We're going to talk about Unit 5.3 right here, Unit 5.3, and we're going to be talking about bond enthalpy. And today what we're going to just talk about really quickly is factors that affect the strength of a bond. Strength of a bond. So what I want you to remember in this case, I want you to say factors that affect, but there are exceptions. So the exceptions. So basically, there are circumstances where some of this is just is false. It's some factors that affect it, but that is not true in every circumstance. So what we're going to see is we're going to see factors that affect bond length. So the factor that we need to know that affects bond length is the atomic radius. So atomic radius. So remember, as we go from the top of the periodic table down, as we go down, the atomic radius increases due to basically more electron shells. More electron shells. So the atomic radius increases as we move down, and it decreases as we move to the right, because the atomic charge in the center gets bigger and bigger and bigger and pulls them in tighter and tighter and tighter. So what we're going to do is we're just going to compare one group. We're going to compare HF, HCl, HBr, and HI. So if you look at your periodic table, we're increasing atomic radius. So fluorine is the smallest, iodine is the biggest, or the largest, as I should have said, the largest, and in between, bromine and chlorine are in between. So basically, as atomic radius increases, bond length, let me erase this. So as atomic radius increases, bond length, right? Bond length increases. So when you're comparing species, and bond length increases, therefore increased bond length means decreased bond strength. And we are going to see some situations in the future when we get to organic chemistry that this may not always be the case. Sometimes fluorine's a better leaving group, sometimes iodine's a better leaving group. And you'd see that, the leaving group means that you have to break a bond. So we will see circumstances in the future where not bond strength is not necessarily decreased, but for this unit, what we need to know is that basically as atomic radius increases, bond length increases, which means a decrease in bond strength. So that's one of the things that we need to know. So if we were to compare a bond between carbon and fluorine and a bond between carbon and bromine, you can say the carbon-fluorine bond is stronger. But we will see later on, like I said, it depends whether we have a polar solvent, it depends whether we have a protic solvent, or it depends if we have an aprotic solvent for how easy this fluorine is going to leave. But that's taking into account more factors. So if we just take into account the atomic radius, we say as the atomic radius increases, bond strength decreases, because in these cases we have to talk about the enthalpy of solvation. So when something gets dissolved, it's an exothermic reaction, so we have to take into account the bond energy in here, but also the bond energy of how much this fluorine wants to leave. If the fluorine gets solvated and releases a lot of energy, that's going to decrease decrease the enthalpy, decrease the bond enthalpy in this case, decrease the total enthalpy of the system. So we're going to see that when we get to our organic chemistry unit. But in this case, all you have to know for now is that as atomic radius increases, bond strength decreases. Okay. So the second one that we need to know is bond strength. We'll talk about bond. I'm going to change the color. I don't want to use this one. I like this color. It's really nice. Bond strength. So what we should know from our last unit is that a single bond is weaker than a double bond, which is weaker than a triple bond. And because what we saw, right, bond length of a single bond is larger than a double, which is larger than a triple. So the shortest bond length is the strongest bond. And that is because, let me erase some of this over here. If we just wanted to look at an alkane, an alkene, and an alkyne, we've got an alkane, an alkene, and an alkyne. So right, sorry, let me just draw this a little bit better. And an alkyne. So, holding these together, right, the positively charged nucleus of this carbon on the right and the positively charged nucleus of this carbon on the left, these electrons are trapped in orbitals here. They're trapped within the pi orbitals above and coming out of the screen. So this is a unit that we covered already and going back into the screen. And the sigma bond in between. So these positive nuclei are attracted to these electrons and these electrons and these electrons. So it starts to pull them closer and closer together because there's so much more. If I were to just erase all of this, if I were to, I am. And so as I am erasing all of this, we were to just draw the electron density. We've got a lot of electron density in this area. So a lot of electron density. So these electrons are repelling each other. But if you imagine, a moment in time, these electrons are all localized around the left carbon. This one's going to be pulling more towards them, saying, oh, give me those electrons back. I want them. So when he pulls them towards himself, he decreases the bond length. He pulls him and this carbon closer together because he wants those electrons that are existing temporarily around this left carbon. And these electrons just exist in random places at random times. So, okay, and the last one that I want to talk about is polarity. I'll change the color now. That's about enough of that color. Polarity. So again, right, we said HF, HCl, HBr, and HI. This is supposed to be an F. That looks a lot like an I. HF, HCl, HBr, HI. We know that hydrofluoric acid is more polar than iodic, right? We talked about the trend in electronegativity. If we were to look at our periodic table, it increases top and right. So as we go up the periodic table from the bottom left to the top right, electronegativity increases all the way up to fluorine, which is the king of electronegativity. So HF is a lot more polar, than HI down here. HI down here. So what we're going to say as polarity increases, bond strength increases. So you can see, right, already there's things overlapping that we typically don't want overlapping, because when things overlap, it means there are going to be exceptions somewhere, right? We said that. Now we've talked about polarity. HF, HCl, HBr, and HI. And we've talked about atomic radius, which is HF, HCl, HBr, and HI. And then we talked about bond strength. So we're going to talk about HF, HCl, HBr, and HI. So we've got all of these things simultaneously overlapping, right? We're trying to say that the polarity of the bond plus the atomic radius equals the bond strength. So we can say, polarity, HF is more polar, therefore it should probably have a stronger bond strength. But also HF has a smaller atomic radius, which means that it also has a bigger bond strength. But in this case, this sets up the mood for exceptions, right? We can have something, let me just erase this. We can have something, this is something that we're considering. What if we have a molecule that is very polar, but has a large atomic radius? So we have something that's very, very polar, but a very large atomic radius, right? Atomic radius should make a big atomic radius should be a weak bond strength, but it's very polar, so it should have a high bond strength. So this is just something that I want you guys to take into account, right? These rules, they are trends, but they're trends that you need to take with a grain of salt, right? Just because it's very polar doesn't mean we can say that it has a high bond strength. And just because it has a large atomic radius doesn't mean it's got a weak bond strength. But the trends that you guys need to just be able to understand here is, you can just deal with them one at a time. And I typically like dealing with them one at a time, because one at a time, these are clear. Okay, as it becomes more polar, bond strength decreases. Okay, that's fine. As it becomes larger, bond strength decreases. Okay, that's fine. So the question should state something, should say based on bond polarity or based on atomic radius, predict the bond strength. Or it can say based off of both, but it should be a clear correlation. It should be a clear, okay, it's highly polar and has it's highly polar and has a small atomic radius. Pretty polar and has a medium atomic radius. And it should make you compare things like this. Because like I said, otherwise there are exceptions that crop up, and then nobody likes exceptions, right? It's exceptions, you learn something and you say, okay, I'm a genius, I know this inside and out, and then they say, except, you know everything except. So that makes things a little bit more difficult. So basically, the trends that we need to know are that as polarity increases, bond strength, and this is the word that chemistry likes to use, tends to increase. So it tends most of the time, but not all of the time. Atomic radius, same thing. As atomic radius gets smaller, bond strength tends to be stronger, but not in every circumstance. So we need to, as a studying chemist, you need to learn this word tends, because it allows for exceptions. It allows for you to, say, oh, okay, well, I didn't know that was an exception, but I left room for it to be an exception, because it tends to increase. You know, it's like you can go back to old Italy, right? Bada bing, bada boom. It tends to increase. Come on, Polly. It tends to increase. Okay, so I hope this video helps you a little bit. Uh, like I said, take everything with a bit of a grain of salt here, because you know, by memorizing these in every single case, you're bound to hit an exception somewhere. So just know that bond strength, you know, the more bonds, the shorter the bond length, the higher the bond strength. This one is pretty clear. This one, you know, there shouldn't be many exceptions. But these ones, there's definitely going to come up with some exceptions in some situations that they may not be completely true in every circumstance. But if you learn the trends that I've kind of talked about, at least you should be able to say, you know what, it tends to have a higher bond strength. You know, it tends to be more polar, but maybe not in every circumstance. Okay, so I hope that helps. I'll see you in the next video, and we'll finish off this unit.